"26 degrees. That is how much cooler a power component ran when the only thing that changed was the material underneath it. No bigger heatsink, no extra copper, no redesigned layout, just the dielectric. A controlled study at the Rochester Institute of Technology measured it, and today we are going to unpack exactly how that happened and what it means for the way you design boards. This is PCB Chat. Hey everybody, I am Andy Shaughnessy. If you have been around the PCB design world for any length of time, chances are pretty good we have crossed paths. Maybe at a conference, maybe you have read one of my articles, or maybe you have just seen me wandering the show floor with a microphone trying to get somebody to talk to me. I have been covering this industry for over 20 years now, and I have to tell you, the thermal management conversation has changed more in the last few years than in the previous 2 decades combined. The power densities designers are dealing with today, they are just brutal, and the old playbook is not keeping up. So when I got a look at the data behind what we are going to talk about today, I thought, well, now we have got to dig into this one. Now, before I bring my guest in, let me take a quick second to thank the sponsor who made today's episode possible. And I will be honest with you, it could not be a better fit. Today's episode of PCB Chat is brought to you by FLIR. Now, if you have ever needed to actually see where the heat is hiding on a board, then you already know FLIR. Their thermal imaging cameras are a staple in electronics labs all over the world. And here's the fun part. That controlled study Chris and I are about to dig into, all of that beautiful temperature data, it was captured with a calibrated FLIR camera. So when you hear those numbers here in a few minutes, well, that is FLIR doing the seeing. To learn more about thermal imaging for electronics design and test, go visit FLIR online. All right, with that, let us get into it. My guest today is Chris Parker, Senior Applications Engineer at TCLAD Inc. Chris has about 30 years of thermal design experience in this industry, and he has been leading the work behind TCLAD's SFL-12 platform, including the validation programs at RIT and CoolCAD Electronics. Chris, it is great to have you on, my friend.
Andy, thanks for having me. I have been a fan of your work for a long time, so this is a good one for me.
Well, I appreciate that very much, and I am really looking forward to this because I think what you all are doing challenges some assumptions that have been baked into this industry for a very, very long time. So let me kick things off with the big picture. For decades, the PCB has basically been treated as the thing that connects components electrically, right? And then thermal management gets bolted on after the fact. Heat sinks, copper coins, fans, thermal vias. Why is that approach starting to hit a wall?
Because we have been working around the real problem instead of solving it. The dielectric, that is the insulating layer between your copper planes, is the thermal bottleneck in most multi-layer boards. FR4 has a thermal conductivity of about 0.3 to 0.4 watts per meter Kelvin. Copper is around 400. So there is this massive mismatch sitting right in the middle of your stack up.
Oh man, so you have got all this beautiful copper that is great at conducting heat, but the layer sandwiched in between is basically acting like a thermal blanket, just sitting there blocking the path.
Exactly. You can pour copper into your design all day, thicker planes, more vias, but if the heat cannot move vertically through the dielectric to actually reach those copper layers, you are not spreading anything. You are insulating. And that was tolerable when power densities were lower. But look at what is happening now. EV power stages, GaN and SiC devices, AI accelerator power delivery, the current densities in these designs are climbing fast, and the dielectric wall is where every one of them hits.
You know, I talk to designers all the time at these conferences, and I hear this frustration constantly. They are doing everything they can with copper and vias and still fighting hotspots. So let me put this in plain terms for anybody listening who is not neck deep in thermal math every day. Chris, you are basically saying the material that most of the industry just takes for granted, The thing nobody even thinks to question is actually the single biggest limit on how much heat your board can handle. Is that fair?
That is exactly it. And the reason it has gone unquestioned for so long is that it worked well enough for the power levels we were dealing with. It does not work well enough anymore.
Hmm. And it is one of those things where once somebody points it out, you think, well, shoot, why did we not look at this sooner?
Right, that is a reaction we get a lot.
All right, so let us talk about what TCLAD did about it. Walk me through the study at RIT because I've read the paper and I think the way this was set up is almost as interesting as the results.
We wanted to isolate the dielectric as the only variable. So we built two electrically identical 6-layer test boards. Same copper weight, same stack-up geometry, same component placement, same loads. One board used standard FR4. The other used our SFL12 dielectric, which runs around 12 watts per meter Kelvin.
Now hold on, let me do the math on that out loud so everybody can appreciate it. FR4 is 0.3 to 0.4. SFL12 is 12. So you are talking roughly 30 to 40 times the thermal conductivity. That is not an incremental improvement. That is a different ballpark.
That is right. And we split each board into 4 quadrants so we could also evaluate surface mount thermal bridges in different configurations. We instrumented everything with a calibrated FLIR camera, validated the imaging against K-type thermocouples, and ran a repeatable power cycling protocol to capture both transient and steady state behavior.
So this was not some rough side-by-side comparison. This was a controlled apples to apples test where the dielectric was genuinely the only thing that changed. I have seen a lot of material comparisons over the years, Chris, and they do not always isolate variables that cleanly. So good on you for that.
That was the whole point. If you change two variables, you do not know which one moved the needle. We wanted clean data that nobody could argue with.
All right, so what did the data show?
In the baseline configuration, no surface mount thermal bridges, the FR4 board peaked at about 144 degrees Celsius. The SFL12 board peaked at about 118.
26 degrees cooler from one material change. Man, that is a number that ought to make every designer sit up in their chair.
It is. And again, no copper change, no geometry change, nothing else in the design moved. That is purely what happens when you stop fighting the dielectric and let the board itself do the heat spreading.
Now, one of the things that really jumped out at me in the paper, and I got a little excited about this one, was the surface mount thermal bridge results. Because I know a lot of designers who lean on those pretty heavily as their go-to thermal tool. What happened when you tested bridges on both boards?
This is one of the most telling findings from the whole study. On the FR4 board, adding 2 surface mount thermal bridges per quadrant gave us about 13 to 14 degrees Celsius of additional reduction. That is meaningful, roughly 5 degrees per bridge. But on the SFL12 board, the same bridges only added about 2 to 3 degrees.
Well, now that is interesting. So the bridges were doing all that heavy lifting on FR4 because the dielectric was so poor. But once you fix the underlying dielectric,
Once the dielectric is no longer the bottleneck, you have already enabled bulk heat spreading across the entire board. The localized solutions, bridges, thermal vias, copper pores, they still have a role, but they shift from being your primary tool to fine tuning. That is a fundamentally different design paradigm.
and I want to make sure that lands for everyone listening. You are not saying thermal bridges are useless. You are saying that when the foundation is right, when the dielectric is doing its job, those supplementary tools become exactly that, supplementary. The hierarchy changes.
That is exactly right.
All right, so the controlled study gives you beautiful, clean, isolated data. Love it. But I know the first thing every engineer listening is going to ask. Does this hold up in a real system with distributed losses and all the messiness of an actual production design?
Right, and that is exactly why we did the second piece with Cool Cat Electronics. We fabricated identical 1 kilowatt bidirectional power converters, one on FR4, one on SFL12. We loaded them at 44 amps with no heat sinks attached, so the only thermal pathway was through the board itself.
No heat sinks at all, 44 amps, and you just let the board handle it. Now that takes some real confidence in your material, Chris.
That was deliberate. We wanted to see what the board alone could do. And we saw about a 9 to 10 degrees Celsius reduction in hotspot temperature on the SFL12 board. But here is the part that I think matters even more. The thermal gradient across the converter, the difference between the hottest and coolest spots, dropped from about 10 degrees on FR4 down to about 3 on SFL12.
Oh, wow. So it is not just running cooler, it is running more uniformly. And I know every reliability engineer listening just perked up because thermal gradients are what kill boards over time.
Yeah, it matters enormously. Uneven thermal distribution is what drives solder joint fatigue, dielectric aging, efficiency drift over time. When you have a 10-degree gradient, different parts of the board are aging at different rates. When you bring that down to 3 degrees, the whole system ages more consistently, and that translates directly to longer service life.
Now, the delta in the real system was smaller than in the controlled test, 9 to 10 degrees versus 26. I am guessing that is expected and not a red flag.
Completely expected. A real converter has distributed losses across multiple devices, transformer losses, parasitics, packaging losses. There are thermal contributions from every direction. The important thing is the directional consistency. The controlled study and the system level result both point the same way, driven by the same physics.
Right, and in a real system, a 9 to 10 degree drop with zero added complexity is still a heck of a win.
It is a big deal, especially when you factor in the gradient improvement.
All right, so this is where I want to zoom out a little bit because I think what you are describing is not just a material swap. It sounds like a fundamentally different way of thinking about the thermal design hierarchy. You call it substrate first. Break that down for us because I think this is the big idea.
For decades, our industry has built a thermal hierarchy that starts at the top and works down. You pick your heatsink first, then figure out copper, then add fans if you need them, and then maybe rethink the layout if nothing else works. The material, the dielectric, is treated as a fixed input that nobody questions.
Right, it is the last thing anyone looks at, if they look at it at all. And I have sat in enough design reviews over the years to know that is the truth.
Exactly. We are saying flip that. Start with the material. That is your highest leverage decision because it addresses the dominant thermal resistance in the stack up. Once you solve that, everything downstream gets simpler. Copper planes and vias become secondary optimization, surface mount bridges and external cooling become fine tuning. And what you end up with is smaller heat sinks, simpler enclosures, higher component density, and better reliability without redesigning the whole system.
So, in a practical sense, a designer who adopts this approach might actually end up with a simpler overall thermal solution, not a more complicated one. That is counterintuitive.
That is the counterintuitive part. A better dielectric does not add complexity, it removes it. You are solving the problem at the root, which means you need less of everything else.
I love that. I'm going to steal that line for a column. Solving it at the root means you need less of everything else.
You go right ahead.
All right, let us get into the nuts and bolts because I know the question on every fabricator's and designer's mind whenever somebody introduces a new material, the very first reaction is, well, that sounds great, but can my fab shop actually run it? Tell us about SFL12 and SFL12G and how they work together.
This is important because they are not two separate competing products. SFL12 and SFL12G are a paired material set engineered to fabricate a standard multi-layer PCB. Together, they act as a drop-in replacement for FR4, but they remove the thermal barrier. From a fabricator's perspective, the build process stays familiar. Lamination, drilling, plating, imaging, etch. The process windows are all within standard ranges.
So you are not asking anyone to retool or invest in new equipment. That is a big deal because I have covered plenty of advanced materials that were fantastic on paper, but never got traction because fabs could not run them without major process changes.
And we were very deliberate about that. Designers keep their stack up and their design intent. The thermal behavior of the finished board is fundamentally different, but the path to get there is not.
What about qualification data? Because a designer who wants to spec this into a production design, especially in automotive or defense, is going to need more than thermal numbers to get it through their review board.
Absolutely. We run through the standard qualification battery, thermal cycling, interconnect stress testing, time to delamination, dielectric breakdown. We publish that data with our applications notes. The RIT and CoolCAD work is the headline thermal study, but it sits on top of a full qualification data set that gives designers and reliability engineers what they need to specify the material with confidence.
Good, because if you cannot get it past the reliability folks, it does not matter how good the thermal numbers are.
Exactly right.
Before we wrap up, and I could honestly keep going on this one, where do you see this landing first in production? What are the applications where substrate first hits hardest?
Anywhere power density is the constraint. EV traction inverters, onboard chargers, DC fast charging, AI infrastructure, where the power delivery stages around accelerators are getting brutal. Defense and aerospace, especially sealed systems where you cannot rely on fans or external heat sinks. And data center power conversion, where every watt of thermal inefficiency turns into cooling load that someone has to pay for.
That is a wide net, but they all share that same fundamental bottleneck.
They do. Too much heat, not enough board level pathway to move it. That is the common thread.
Chris, for listeners who want to dig into the data or evaluate the platform on their own designs, what is the best next step?
Reach out to TCLAD Inc. directly. We have multiple solutions for resolving thermal design challenges, and our applications team will work with you on stack up, fabrication path, and qualification. The published RIT and CoolCAD data is a great starting point, but the conversation about your specific design is where the real value comes in.
Chris Parker, Senior Applications Engineer at TCLAD Inc. This is a really good conversation. Thanks for spending the time with us.
Andy, my pleasure. Thanks for having me on.
That was Chris Parker of TCLAD Inc. The full technical paper, Thermal Performance Enhancement in Power-Dense Electronics Using High Conductivity PCB Dielectrics, is available through Circuits Assembly. To engage TCLAD directly on your thermal design challenges, visit tclad.com. I'm Andy Shaughnessy. Thanks for listening, everybody.